Happy New Year, everyone, and welcome back. We are so excited to be kicking off a brand new season of Saltwater Stories.
It feels amazing to be back. For the past 2 seasons, we've had so much fun sharing all these stories about the ocean.
We really have. And it's been incredible to see so many of you from all over the world listening in every week.
It is. The community that's sort of grown around this is just fantastic.
It really is. And you know what's amazed us the most is how so many of you just stumbled on the show and decided to stick around.
Right. So we were thinking over the holidays, how can we help more people who love the ocean find these stories?
And the best idea, and I love this, came from our interns.
It really did.
Yeah.
So this season, we're going to try something a little different. We're going to venture out beyond the show itself, but we'll tell you a lot more about that at the end of today's story.
Okay, season 3 starts right now. And today's story, well, it isn't just a story. It's this huge question, really. The one we probably should have started with on day 1.
It's the biggest, wettest mystery of them all. We're going on a search for the secret history of our planet's water.
It's the origin story, and it doesn't start in the ocean. It starts with fire and with space and with our dusty red neighbor.
Exactly. When you see Earth from space, it's this stunning blue marble, right? Just this beautiful sapphire jewel.
Covered in water. More than 70% of our planet is ocean. It makes us so unique.
But then you look next door to Mars,
Mm.
and it's just red and dusty and dry.
The difference is just, it's huge. And that difference has fascinated people for a very long time.
Oh, yeah. Long before we could send robots or rovers, people were pointing telescopes at Mars, trying to figure it out.
Which brings us to this really fun story. It's about an astronomer named Percival Lowell, way back in 1909.
Right, Lowell. He was a wealthy guy, and he was completely obsessed with Mars. He built this giant telescope up on a mountain in Arizona.
And when he looked through it, he didn't just see a red dot. He saw lines all over the surface. He started drawing these incredible maps.
He called them great waterways and canals. He even drew spots he called oases. And he noticed they seemed to change with the seasons on Mars.
So he looks at these lines crisscrossing the planet, and he thinks, that doesn't look natural.
He came to this amazing conclusion. He decided they had to be huge engineering projects built by Martians.
By Martians, he actually thought that.
He was convinced. He imagined this dying civilization, right?
Yeah.
Their planet was drying up, and they were building this massive network of canals to move water from the ice caps at the poles down to their cities.
Wow. That is an incredible story. It's no wonder people got so excited about Mars.
Oh, you captured everyone's imagination. But, science moves on, and eventually we got a closer look.
Right. The sad truth. When the Mariner robot probes finally got to Mars, almost 70 years later,
No canals, and definitely no Martians.
they did find something else. Something maybe even more incredible.
They confirmed that Mars used to have water. Lots of it. We can see the outlines of ancient rivers, huge canyons carved by massive floods, minerals that can only form in water.
So Mars was once a blue world, too.
It seems so, which leads to 2 huge questions. What happened to all of Mars's water? And the big one for us today.
Where did all of Earth's water come from in the first place? How did we get so lucky?
Exactly. Because when you look at how our planet was born, it seems like water should have been impossible.
We call Earth the Goldilocks planet, right? Not too hot, not too cold, just right for liquid water.
But it was not born that way. Not at all. When Earth was a baby, it was more like Venus. A hot mess.
Let's go back, way back, about 4.5 billion years ago. Our whole solar system was just this big, swirling cloud of gas and dust, the solar nebula.
You think of it like a giant, messy construction site floating in space.
Wow.
And gravity, that invisible force, starts pulling things together.
So tiny bits of dust clump into pebbles. Pebbles stick together to make rocks.
And the rocks smash together to make boulders. And then those boulders form what we call planetesimals, which are like baby planets.
This whole building process has a name, right?
Yep. It's called accretion. It's like rolling a snowball downhill. It just keeps picking up more and more stuff and getting bigger.
But this wasn't a quiet, snowy process. Every single time one of those rocks hit the baby Earth, it was like a huge explosion.
1 billion tiny explosions, all releasing a massive amount of heat. And that wasn't the only source of heat.
Oh, right. Inside the planet, there were all these radioactive elements, kind of like tiny little furnaces, all giving off energy.
So all that heat added up. The surface of the Earth reached over 3,000 degrees Fahrenheit.
That is unbelievably hot. I can't even picture that.
It's so hot that the entire planet was melted. The surface wasn't solid rock, it was a magma ocean.
A magma ocean, so a whole sea of glowing red melted lava.
Exactly, churning and bubbling. There was no solid ground anywhere.
That sounds terrifying.
That's why we call that time the Hadean. It's named after Hades, the Greek god of the underworld. It was a pretty hellish place.
Okay, so that's the whole mystery then. If the planet was a giant ball of fire, how could it possibly have water?
You couldn't. If you tried to pour a glass of water onto Hadean Earth, it wouldn't even sizzle. It would just instantly flash into steam and be gone. Poof. Any water that was in those original building block rocks should have just boiled away and been lost to space. It seems like Earth should have been born completely dry.
And as if that wasn't enough, just when things might have started to cool down a little bit.
The universe delivered the biggest punch in our planet's history. We call it the Big Splash.
This was the collision with Theia.
Right. About 4.5 billion years ago, another baby planet about the size of Mars, which we named Theia,
Smashed right into Earth.
a direct hit. The energy from that was just unimaginable. It melted the entire planet all over again.
And it blasted all this debris, this rubble from both Earth and Theia out into space.
And all that rubble, over time, was pulled together by gravity to form our moon.
So this was like a giant reset button. Any tiny bit of water Earth might have held onto, gone.
It should have been. That impact should have vaporized it all and sent it flying so far away that it just disappeared into space.
Okay, but it didn't disappear completely, did it? Where did the water molecules go?
They turned into gas, into steam. And this is where the rocks themselves become important.
You mean outgassing?
Exactly. The planet was covered in volcanoes, and these volcanoes were constantly burping out huge clouds of gases that were trapped inside the melted rock.
And one of those main gases was steam. Water vapor?
A lot of it, along with carbon dioxide and ammonia. This created Earth's very first atmosphere.
Which was basically a super thick, super hot, high-pressure steam sauna.
Pretty much. All the water was in the sky, not on the ground. It was trapped up there, just waiting for the planet to finally cool down.
So to figure out where that steam came from originally, scientists needed some kind of, I don't know, a detective kit?
That's a perfect way to put it. They needed to find the water's chemical fingerprint, its secret identity.
Hydrogen and oxygen.
Right. Hydrogen's super common, made in the Big Bang. Oxygen's a bit heavier, made inside stars. They bond together.
But the secret is that not all hydrogen is the same. There's a secret flavor.
Yes, and this is so cool. It all comes down to something called isotopes.
Okay, so what's an isotope?
So imagine normal hydrogen is like a tiny, light little marble. We call that protium. Well, hydrogen has a heavy cousin, and its name is deuterium.
A heavy cousin.
Yep, it's like the same marble, but it has a tiny extra weight glued onto it, a neutron. This makes it twice as heavy as normal hydrogen.
So when a water molecule forms, it could use the normal hydrogen or it could grab the heavy cousin.
Exactly. And that makes what we call heavy water. We can't see it or taste the difference, but scientists can measure it very precisely.
They measure the ratio, like how much heavy water there is compared to normal water.
You got it. It's called the DH ratio, the amount of deuterium, DD, to the amount of normal hydrogen, H.
And here's the detective trick, right? That ratio, that flavor, is different depending on where in the solar system the water came from.
That's the key. Water that formed way out in the cold, dark parts of the solar system has a much heavier flavor, a higher DH ratio.
So our oceans have their own specific flavor.
A very specific recipe. And by comparing that recipe to the water we find on space rocks, we can figure out where our water was cooked up.
Okay, that makes sense. But what about the other main ingredient in the ocean? The salt. Did that come from space too?
No. The salt is a totally different story. That was an inside job, 100%. The salt came from right here on Earth.
So the first rain that ever fell, it was fresh water.
Completely fresh. The saltiness built up over billions of years. It starts when rain falls through the air.
Okay.
It picks up a little bit of carbon dioxide from the atmosphere, and that makes the rainwater just slightly acidic, like super, super weak vinegar.
And that acid rain falls on the rock.
And it slowly breaks them down. It's a process called weathering. As the rocks break down, they release all the little minerals trapped inside them.
Including sodium and chloride, the two parts of salt.
The very same. And then the rivers act like big conveyor belts, washing all those dissolved minerals from the land down into the ocean.
But wait, why doesn't the salt just wash back out again? Why does it build up?
Because of the sun. When the sun shines on the ocean, it heats up the water, and the pure water molecules evaporate. They turn into steam and float up to make clouds.
But the salt is too heavy, it can't evaporate.
The salt gets left behind.
Yeah.
Every single time. So for billions of years, rivers have been dumping in a tiny bit of salt, and the sun has been taking out only the pure water.
So the oceans just got saltier and saltier and saltier.
Exactly. And that's why it's so much easier to float in the ocean than in a lake. All that salt makes the water heavier and more dense.
And we can't forget those hydrothermal vents, the underwater chimneys.
Right. They're part of the recipe, too. They're constantly pumping out hot water full of different chemicals and minerals from inside the Earth's crust, helping to stir the pot and keep the ocean's chemistry balanced.
Okay, so we have our detective kit, the DH ratio. And for a long time, the main theory was that Earth started out totally dry and the water had to be delivered.
Yep. Theory 1. The Space Delivery Service. Or, as scientists call it, an exogenous source, meaning it came from outside.
And this delivery happened during a really chaotic time, right? The late heavy bombardment.
It was cosmic chaos. We think the giant planets, Jupiter and Saturn, shifted their orbits a little bit. And when they moved, their huge gravity was like a slingshot.
Flinging millions of asteroids and comets from the outer solar system right towards us.
A cosmic pinball machine. So the detectives had two main suspects for who was carrying the water.
Suspect A comets. The famous dirty snowballs.
They seem like the perfect culprits. They're from way out past the snow line where it's super cold, so they're mostly made of ice and dust.
If enough of them hit Earth, that's a lot of water.
It would have been more than enough. But then we used our detective tool.
This was the Rosetta mission, right? It actually flew to a comet.
An amazing mission. It visited Comet 67P and basically sniffed the water vapor coming off of it.
And the verdict was?
The water was too heavy.
Too heavy.
It had 3 times the amount of deuterium, that heavy hydrogen, as our oceans do. The recipe was completely wrong.
So the fingerprint didn't match at all. Comets were not our water delivery guys.
Well, they maybe delivered a little bit, perhaps 10%, but they weren't the main source. So we had to move on to suspect B.
Asteroids.
Specifically, a type called carbonaceous chondrites, C-type asteroids.
Now, I always think of asteroids as just dry, gray space rocks.
Most of them are. But these C-types are different. They're not puddles of water, but they're more like a really hard, wet sponge or a big ball of damp clay.
So the water is trapped inside the rock itself.
Chemically locked into their minerals. They're called hydrated minerals. And some of these rocks can be up to 20% water by weight.
20%? That's a lot for a rock.
It's a huge amount.
Yeah.
So the next question was, how did these wet sponges get from the asteroid belt all the way to Earth?
Jupiter, the big bully.
Jupiter, the pinball flipper. The theory is called the grand tack. Jupiter moved around a lot in the early solar system, and its gravity just flung these wet asteroids inwards, right into our path.
An accidental water delivery service.
A very effective one. And here's where it all clicks. When scientists get meteorites on Earth that we know came from these C-type asteroids,
They test the DH ratio.
and it's a perfect match. The flavor of the water in those asteroids is almost exactly the same as the water in our oceans.
The recipe is right.
The recipe is right. And we've even gone and collected samples now. NASA's OSIRIS-REx mission to the asteroid Bennu and Japan's Hayabusa 2 mission to Ryugu.
And they confirmed it.
Absolutely.
Yeah.
They brought back these little bits of asteroid, and they are full of water-rich clay and all sorts of organic materials, the building blocks of life.
So it seems like a done deal. Asteroids delivered our water.
It was a leading theory for a very long time. But what if Earth didn't need a delivery service at all?
What do you mean?
What if the water was here from the very beginning, baked right in? Theory 2, the inside job.
The endogenous source. So the water was part of Earth's original ingredients.
Exactly. To check this idea, you have to look at the actual rocks that built Earth in the first place. They're a type of meteorite called enstatite chondrites.
Okay, and for a long time, scientists thought those rocks were totally dry, right?
Bone dry.
Yeah.
Because they form close to the sun, where it was too hot for ice to form. It just made sense.
But then our technology got better.
Much better. Starting around 2020, new techniques allowed scientists to look at these dry rocks with incredible detail.
And they found something surprising.
A huge surprise. They found that these rocks had enough hydrogen trapped inside them to fill Earth's oceans at least 3 times over.
3 times. So the ingredients were there from day one.
Earth was born wet. The planet had the recipe for water baked into its crust and mantle from the very beginning.
So that steam in the early atmosphere, the stuff coming out of volcanoes.
It was coming from the rocks of Earth itself. The planet was making its own water.
Okay, that's amazing. But the story gets even crazier, doesn't it? The idea that the oceans we see are just the tip of the iceberg.
You could say that. It's the discovery of the deep Earth sponge,
This came from a diamond.
a very special diamond that was shot out of a volcano. And inside that diamond, scientists in 2014 found a tiny bluish mineral called ringwoodite.
And ringwoodite is the sponge.
It acts just like one. Its crystal structure is perfect for trapping water ions. Not liquid water, but the tiny building blocks of water, chemically stuck to the rock.
And this diamond came from super deep.
About 400 miles down from a layer we call the transition zone.
So it's not a big swimming pool of water down there?
No, not at all. It's
Ah.
more like a very, very damp rock under extreme pressure. But when they did the math,
The numbers were huge.
the numbers were staggering. That one layer of the Earth, the transition zone, might hold 3 times more water than all of our surface oceans combined.
3 times more. So Earth isn't just a planet with oceans on it. It's a water planet through and through.
It's fundamental to our entire structure. And there's this giant slow recycling system going on.
The deep Earth water cycle.
Right. Tectonic plates slide down into the mantle in a process called subduction, and they drag ocean water down with them.
And then volcanoes bring it back up again.
Exactly. Outgassing. This huge, slow loop keeps the amount of water on the surface remarkably stable over billions of years.
Okay, so this is blowing my mind. We have the inside job, where Earth made its own water, and we have the space delivery service, where asteroids brought it. Which one is right?
Well, like with a lot of big questions in science, the answer is both.
It's a hybrid model.
It's a hybrid model. The best way to think of it is like baking a cake.
Okay, I like cake.
The base of the cake, the main ingredient, probably 60 to 80% of our water, was the inside job. Earth's own rocks provided most of it through volcanoes.
And the seasoning, the frosting.
That was the space delivery service. Those wet asteroids came in later and topped it off, adding the final 20 to 40%. And they also brought all those nice organic sprinkles needed for life.
I love that, a water cake. So let's put the timeline together. How did we go from a giant steam sauna to actual liquid oceans?
It happened surprisingly fast.
Oh.
So 4.5 billion years ago, after Theia hit, we have the magma ocean and the steamy atmosphere.
Then came the great cooling.
Around 4.4 billion years ago, the planet finally cooled enough for a solid crust to form, like a skin on top of a pot of soup.
And the temperature on that crust dropped below the boiling point of water.
Below 212 degrees Fahrenheit. That was the moment the atmosphere was waiting for.
And then it rained.
And it rained, and it rained. This was the Great Deluge. It wasn't a shower. It was a nonstop torrential downpour that may have lasted for thousands of years.
Wow. Just constant rain filling up all the low spots on the new crust.
That endless rain formed the very first oceans. The sound must have been incredible. Just a constant hiss of water hitting hot rock.
And we know this happened so early because of tiny time capsules.
Tiny, super tough crystals called zircons. Scientists found some in Australia that are 4.4 billion years old. The oldest bits of Earth we've ever found.
And what's inside them?
They analyzed the oxygen trapped inside the crystals, and its chemical signature proved that these little crystals could only have formed in cool, liquid water.
So oceans were here really, really early.
Much earlier than we used to think, Earth became a water world almost right away.
But those first oceans didn't look like our blue oceans today, did they?
No, not at all. They were probably a murky, greenish color
Green. Why green?
because they were full of dissolved iron. That early acid rain was breaking down the volcanic rocks and washing tons and tons of iron into the water.
And there was no oxygen to make it rust.
Exactly. So the iron just stayed dissolved in the water, turning it green.
So what turned the oceans blue?
Life itself. Around 2.4 billion years ago, tiny microscopic life forms called cyanobacteria figured out photosynthesis.
They started breathing out oxygen, the great oxidation event.
And that oxygen was like poison to the green, iron-rich ocean. It reacted with the iron and made it rust.
So the whole ocean rusted.
The whole ocean rusted. All that rust, which is iron oxide, was heavy, and it sank to the bottom of the seafloor, cleaning up the water.
And once the iron was gone, the water became clear and blue.
The blue narwhal was born.
That is just the best story. And it's so important because without that water, there would be no us.
Water is the cradle of life. For the longest time, we thought life started in some warm little pond on the surface.
But the surface was a mess back then. Asteroids, radiation.
Total chaos. So now a lot of scientists think life began in the deep, dark, quiet ocean.
At the hydrothermal vents.
Specifically at the cooler, gentler vents, the white smokers, like the ones in a place called the Lost City in the Atlantic.
And it's the chemistry there that's so special.
It's perfect. The warm, alkaline water from the vents, mixing with the cold, acidic ocean water, creates this natural energy source in the tiny pores of the rocks.
Like a little battery.
A tiny life-giving battery. It's the perfect, safe nursery for the first simple organic molecules to form, protected from all the craziness up on the surface.
So the ocean didn't just have life, it helped create it. But why did we get to keep our oceans when Mars and Venus lost theirs?
It all comes down to luck and protection. Let's look at Venus first, Earth's evil twin.
It's so hot there you could melt lead.
And bone dry. But it probably started with oceans. It was just a little too close to the sun. The oceans started to evaporate, creating water vapor.
Which is a greenhouse gas. It traps heat.
A really powerful one. So the more water evaporated, the hotter it got. The hotter it got, the more water evaporated. It's called a runaway greenhouse effect.
It just boiled its own oceans away.
Boiled them away, and then sunlight zapped the water molecules apart, and the light hydrogen just escaped into space. Game over for Venus.
And Mars, the freeze-dried planet.
Mars had the opposite problem. It's just too small.
Too small.
Because it's smaller, its hot, liquid core cooled down and solidified much faster than Earth's.
And when the core stops spinning,
It loses its magnetic field, its protective shield.
the shield that protects us from the solar wind.
That constant stream of particles flying off the sun. Without a shield, the solar wind just slammed into Mars's atmosphere for billions of years and stripped it all away.
And the water went with it.
Evaporated into space or froze underground.
So Earth's secret weapon is our big, hot, spinning core.
It's what generates our powerful magnetic shield. It protects our air and our water. We stayed in the Goldilocks zone, and we had a shield. We got really, really lucky.
And we're still learning more. Those samples from the asteroids Bennu and Ryugu confirm they didn't just bring water, they brought amino acids.
The building blocks of life. They were delivering the water and the construction kit at the same time.
And now we're looking for water on other worlds, like Jupiter's moon Europa.
Exactly. The Europa Clipper mission is heading there to study the huge ocean we think is hidden under its ice shell.
Yeah.
Understanding our own story helps us know where else to look for life.
What an incredible journey. From a sea of fire to a world of water.
It really is. So, to recap our big mystery, we found 5 key clues that solve the case.
Okay, what's number 1?
First, Earth was born wet. The ingredients were baked in from the start.
Second, asteroids help top it off, bringing extra water and the ingredients for life.
Third, the mantle is a giant sponge, holding a huge hidden ocean deep inside the planet.
Fourth, Earth got lucky. Our size and our magnetic shield protected our water.
And fifth, that water became the cradle of life, with deep-sea vents acting as the perfect nursery.
Thank you so much for joining us on this amazing exploration of our liquid history. It really makes you see water in a completely different way.
It does, and here's a final thought to leave you with. The water you drink today in your glass. It's the same water that fell in the Great Deluge 4.4 billion years ago.
It's the same water the dinosaurs drank.
The very same. This water didn't just come from a lake. It came from the fire of our planet's birth and the chaos of space.
Knowing that, what does it mean for how we should protect every single drop? That's something to think about this week.
Now, just circling back to what we mentioned at the start, our plan to spread the word about saltwater stories.
Right. We want to meet people where they are, and that seems to be on social platforms. So this season, we're going to dip our toes in and test the waters there.
You can expect to see some short, thoughtful, science-grounded stories and insights from us. We're promising curiosity and context, not just chasing attention.
And you can really help us out. If you see our stuff, giving it a like, a comment, or a share would mean the world to us. Following us helps a ton too.
The links to those new channels are right there in the episode description.
We'd love to see you there.
Once again, thanks so much for tuning in. We can't wait to have you back next week for another incredible story here on Saltwater Stories.
Bye for now. Take care.